Welcome back. In this lecture, we will look at how to think through the maximum power which you get from a fuel cell. Power depends on two quantities that are related to each other. Power, in a simple form, is expressed as VI. While the current drawn from a fuel cell increases, the voltage delivered by a fuel cell decreases. So these are two interrelated quantities. In a narrow regime of fuel cell operation, as given, let's say, from a polarization curve, this variation, that is the variation of voltage with I, is nonlinear. That is only in a narrow region. That is, when you're at low current, you are in the activation over potential region, or when you are in very high current, you are in the concentration or transport over potential region. In this region, VI has a nonlinear dependence. But in most cases, in the operational region is not in these two extremes. The variation of potential is linear. So as I increases, V decreases. This is an useful feature for simplifying the analysis of maximum power. So whenever you have this linear dependence, you are in the ohmic region, because of the way ohmic resistance behaves. We see this behavior as I increases, V falls linearly. So we've already seen the potential that you get from a fuel cell can be expressed in this manner. So all these over potentials, that is both the activation over potential and the concentration over potential, can be clubbed together and can be expressed in this manner. That is, the voltage which you obtain from a fuel cell is approximately equal to the open circuit potential minus the ohmic loss minus all the other potential. So why do we do this? It helps you to simplify the relationship. Power is VI. So we put this expression into power, and then to get the maximum power, we have to have the condition, that is, the first derivative of power with respect to current is 0. From that, we can get, from a simple manipulation, we will get the potential at maximum power, which is expressed in this manner. Because you are in the ohmic region, we can substitute, once you know the potential, what is the current at maximum power. Why is this important? This behavior important? This kind of analysis is important, is because remember, if you have maximum voltage, that is only at open circuit potential. I is 0 at open circuit potential. Power is 0 when you have maximum potential. On the other extreme, when you get the maximum current in the transport over potential region, your voltage that from a fuel cell is close to 0. Again, when you have maximum I, V is 0, therefore P is 0. So you do not want to be in either of the extremes. You are somewhere in the middle in the ohmic polarization region. So from this, you can simplify the power max by plugging all these things in and obtain this relationship. Why is this form of relationship convenient? Because in the ohmic region, you are already measuring this. Okay, so even without explicitly obtaining the open circuit potential, we can get a measure of these quantity. And as the current changes, with decrease in potential, you can get the resistance also. So implementation of this formula is quite easy when it comes to a fuel cell, especially in the operational regime, which is in the ohmic polarization regime. In the next lecture, we will look at the electrode structure in a fuel cell. Uh, Again, we have looked at similar themes when we looked at porous electrodes in the context of batteries and capacitors. We will place that topic in the context of fuel cell. That will be done in the next lecture. Thank you.